Salam sejahtera kepada semua para pelajar sekalian. Selamat datang ke Magic Revision Siri 2. Apa khabar para pelajar sekalian? So harap semua berada dalam keadaan baik dan boleh bersedia untuk meneruskan sesi perkongsian malam ini. Sebelum memulakan sesi perkongsian malam ini, so saya ingin memesan pelajar boleh tinggalkan komen soalan di live chat YouTube, dan selepas sesi ini para pelajar boleh isi soal selidik untuk program ini. So tanpa membuangkan masa, so kita menjemput Mdm Tang, calon pensyarah cemerlang Kolej Matrikulasi Selangor. Tajuk yang akan disampaikan oleh Mdm Tang ialah Chemical Bonding Part 1. So di mana Mdm Tang akan menyentuh tajuk Lewis Structure dan Molecular Shape. So dipersilakan Mdm Tang untuk sesi perkongsian malam ini.
Madam Chia, so we shall move on to tonight's session. So the revisions on chemical bonding part 1, and I'm going to focus on Lewis structure and molecular shape and polarity. So we move on to look at the Lewis structure first. For Lewis structure, basically there are 4 steps to draw the Lewis structure. So first step is to calculate the total number of valence electrons. So if you are being given positively charged ion, you just need to need to minus the electron equal to the charge of the ion. And if you get negatively charged ion, you need to add the electrons equal to the charge of the ion. So in step number 2, you draw the skeletal structure. So the least electronegative atom must be put as the central atom except hydrogen. So step number 3, you need to make the terminal atom octet except hydrogen, and remaining electrons must be put on the central atom. So for step number 4, you need to make the central atom octet by using the lone pair of the terminal atoms to form the multiple bonds, except beryllium, boron, and aluminium as the central atom, then we can have incomplete octet. So basically, these are the 4 steps to draw the Lewis structure. And in 4.1, you also learn about octet rules. So what is octet rules? So basically, octet rules refer to the atoms with 8 electrons around it. And then you also learn the exceptions to the octet rules. So the first one is the incomplete octet, where you can have the beryllium, boron, and aluminum as the central atom, and the central atom with boron, beryllium, or aluminum has less than 8 electrons around the central atom. So if that is the case, then we have incomplete octet. So the second exceptions to the octet rules would be the odd electron molecule. So how do you know that you are getting odd electron molecule? In step 1, when you calculate the total number of valence electron, if you get odd number, means that you are going to get odd electron molecule. And for expanded octet, usually occurs when the period 3 or beyond elements become the central atom. So period 3 and beyond elements, because they are d orbitals available to put the extra electron, that's why when they become the central atom, possible to have expanded octet where there are more than 8 electrons around the central atom. And then in 4.1, under the subtopic Lewis structure, you also learn about formal charge. So this is the formula to calculate formal charge. So formal charge equal to the valence electron minus the sum of the lone pair electrons with half the bonding pair's electron. So from the formal charge, usually we want to determine which one is the most plausible Lewis structure. So the first priority is for neutral molecule. The first priority is having the 0 formal charge on all the atoms. If we can't get 0 formal charge on all the atoms, then we go to the second priority where the formal charge on each atom is lower possible. So the lower formal charge means that it's the one closer to 0. And the third priority would be the negative formal charge must be put on the more electronegative atom. We will look at more examples after this. So for example 1, ClCN here. So ClCN has 3 possible Lewis structure. And then the questions want you to determine which Lewis structure is the most plausible Lewis structure for ClCN. So to do this, again, we need to draw the Lewis structure for ClCN first. To draw the Lewis structure, you just need to go through the 4 steps. So step number 1, you calculate the total number of valence electron for ClCN. So the total number of valence electron is 16. So step number 2, you need to draw the skeletal structure. So for to draw the skeletal structure, the least electron negative atom, so here is the carbon, must be the central atom. So the carbon be the central atom. So this is the skeletal structure for ClCN. And then in step number 3, remember, you need to make the terminal atoms octet. Okay, so just now after step number 2, I already draw 4 electrons, so -4. So 12 electrons remain. So in step number 3, need to make the terminal atoms octet. So just put in the electrons. So I have drawn all the 12 electrons. So no electrons remain. So means that no electrons you need to put at the central atom. But then after step number 3, can you see that the central atom carbon here is not yet octet? So how can we make it octet? So remember in step number 4, if we want to make the central atom octet, we can use the terminal atoms, long pairs. So here we have chlorine. So we can use the chlorine lone pair. Okay, 1 lone pair to form a double bond. Okay, so look at our central atom carbon is still not yet octet. So we can use another lone pair on chlorine to make triple bond. So can you see that now the central atom carbon having 8 electrons around it, so it's octet. So this is the first possible Lewis structure for ClCN. So besides having besides having the lone pair, use the lone pair on Cl to make triple bond, we can also use the lone pair on nitrogen to make another double bond between carbon and nitrogen. And this also allowed the central atom carbon to be octet. So means that this is the second possible Lewis structure for ClCN. Okay, so just now we have looked at using the lone pair on chlorine and 1 lone pair on nitrogen. So besides this, we can also use all the 2 lone pairs from the nitrogen to make triple bond between carbon and nitrogen. So this also made the central atom carbon octet. So this gives us the third possible Lewis structure for ClCN. So these 3 Lewis structure of ClCN, so basically they are resonance structures to one another. So since they are resonance structure, we can use the double-headed arrow to write them, okay, to represent them as the resonance structures to one another. And the second part of the question asks us to determine which of these Lewis structures is the most possible Lewis structure. To determine the most possible Lewis structure, we need to calculate the formal charge. So how to calculate the formal charge for structure 1? So again, we need to use the formal charge formula, valence electron minus the sum of the lone pair electrons with the half bonding pairs electrons. So for this, we can first calculate the formal charge for chlorine. So chlorine valence electron is 7. So 7 minus 2 lone pairs electron plus half bonding pair electron. So half bonding pairs, so how can you calculate this? So my method is cover half of the bonding pairs and you only count the electron that belongs to chlorine. So after you cover half of the bonding pair, so only 1, 2, 3 electrons that belongs to the chlorine. So means that the half bonding pair electrons here is 3. So this will give the formal charge for chlorine as +2. Okay, do the same thing for carbon. So how do we calculate the formal charge for carbon? Also the same thing, carbon, the valence electron is 4, so 4 minus lone pair electrons. There is no lone pair electrons around carbon, so it's 0 plus half bonding pair electron. So this half bonding pair, so basically for the bonding pairs electron, you just cover them. Okay, cover them, so become half, and then only count the electrons that belongs to the carbon. So how many electrons belongs to the carbon? So 1, 2, 3, 4. So 4 to give formal charge of carbon equals to 0. Okay, so repeat the same thing for nitrogen. So nitrogen, so 5 valence electron minus lone pair electrons, we have 1, 2, 3, 4, 5, 6. So minus 6 plus half bonding pair electron. So you can cover half. So how many electrons belong to nitrogen? So only 1. So 1 here. So to give the formal charge of nitrogen as -2. So this is the formal charge for structure 1. Can you see that it is not lower possible? So we are not sure whether this one is the most plausible Lewis structure or not. So we move on to calculate the formal charge for structure 2. So how to calculate the formal charge for structure 2 is also the same thing. Use the formal charge formula. So for chlorine, valence electron 7. So 7 minus lone pair electron 1, 2, 3, 4. So 4 plus half bonding pair electron. So you can cover half of the bonding pair electron. So and then count how many electrons belongs to the chlorine. So 1, 2. So only 2 belongs to the chlorine. So means that the chlorine here having the formal charge of +1. And then for carbon, again 4 valence electron minus around carbon there is no lone pair, so 0 plus half bonding pair electron. So you cover the bonding pairs around carbon by half and only count the electrons that belongs to carbon. So which is 1, 2, 3, 4. So it's 4. Therefore, the formal charge of carbon here in structure 2 is equals to 0. And for nitrogen, okay, so nitrogen, so valence electron is 5. So minus the lone pair electron, 1, 2, 3, 4. So minus 4. And then for half bonding pair electrons, so we cover the bonding pairs of nitrogen by half and only count the electrons that belongs to nitrogen. So that is 2. So plus 2. So to give us the formal charge of nitrogen equal to -1. Okay, so we are not sure whether this is most plausible structure or not. So we continue to calculate the formal charge for the third structure. So for the third structure, also the same thing. So calculate the formal charge for chlorine, 7 valence electron minus the lone pair electron, 1, 2, 3, 4, 5, 6. So 6. For the half bonding pair electron, you just need to cover the bonding pair electrons by half and only count the electrons that belong to the chlorine. And here is 1. So 1. So to give 0 formal charge of chlorine in structure 3. And then for carbon, also do the same thing. So 4 valence electron. There's no lone pair electrons around carbon. And then half bonding pair electrons, so cover the bonding pair electrons by half and only count the electrons that belongs to the carbon. So there is 1, 2, 3, 4. So 4 to give 0 formal charge for carbon. And for nitrogen, also the same thing. So nitrogen, 5 valence electron minus 1, 2, 2 lone pair electron plus half bonding pair electrons. So half bonding pair, you cover the bonding pair electrons by half and only count the electrons that belongs to the nitrogen, which is 1, 2, 3. So 3 to give 0 formal charge on nitrogen. So from this, straight away we can decide that structure 3 is the most plausible Lewis structure because remember for neutral molecule, the first priority is going to the 0 formal charge on all the atoms in the molecule. So structure 3, this is the most plausible Lewis structure because 0 formal charge on each of the atoms. While for structure 2 and structure 1, the formal charge on each of the atoms is not as lowest as in structure 3. Structure 3 having 0 formal charge on each of the atoms, so this one is the most plausible Lewis structure for ClCN. Now we move on to look at the second example. So draw the possible Lewis structure for bromate ion, BrO3- and determine which of the Lewis structure is the most plausible Lewis structure for bromate ion. So for this, again, we need to draw the Lewis structure first. So step number 1, we need to calculate the total number of valence electrons. And for bromate ion is 25, but because this one is ion, -1, don't forget we need to add 1 electron, okay, which is equal to the charge. So to give total valence electrons of 26. Then we can move on to step number 2 to draw the skeletal structure. So bromine and oxygen, bromine is less electronegative. So in step number 2, we use the bromine as the central atom. So this is the skeletal structure of bromate ion. Because this is ion, so don't forget to put the bracket and also the charge. Now I have drawn three bonding pairs, so that is 6 electrons. So I have drawn 6 electrons, so -6, so 20 electrons left. So in step number 3, we want to make the terminal atoms octet. So put all the electrons in to make the terminal atoms octet. So that is 18 electrons, so -18. So 2 more electrons remain, and this remaining electron must go to the central atom, and here is the bromine atom. Okay, and then can you see that after step number 3 for bromate ion, okay, so we already the central atom, bromine, is already octet, already having 8 electrons around it. So since already have 8 electrons around it, so we don't straight away rush to draw the multiple bonds around the bromine. Okay, we must, since after step number 3, bromine already octet, so we should the next step we should do is we need to calculate the formal charge first before we move on to draw the multiple bonds. So so this is the structure that we draw after step number 3. So is this the most plausible Lewis structure for bromate ion? So we are not sure. So if we are not sure, since the central atom already octet, then what we need to do next is to calculate the formal charge first. Okay, so how do we calculate the formal charge? Just need to use the formal charge equations. So for bromine here, again, 7 valence electron. So lone pair electron, so there are 2. Okay, so there are 2, so minus 2. Okay, plus half bonding pairs electron. So remember, half bonding pair electrons, so all the bonding pair we can, at bonding pair electrons, we can cut half and then only count the electrons that belongs to the bromine. And here is 1, 2, 3. So it's 3. So this gives the formal charge on bromine as +2. While for the oxygen, there are 6 valence electrons. And then around the oxygen, there are 1, 2, 3, 4, 5 6. So there are 6 lone pair electrons. And for the bonding pairs electron, we cut half and only count the electron that belongs to oxygen. So that is 1. So 1. So this gives -1 formal charge on oxygen. Can you see that all these 3 oxygens are the same? So it means that all of them having the formal charge -1. While for the bromine, it is +2. So can you see that bromine here in structure 1 is +2, while the terminal atom oxygen are -1. So means that here in structure 1 is not yet the lower possible formal charge on the atom. So what we can do next is we can draw the multiple bond using the lone pair on the terminal atom. We can use the lone pair on the terminal atom to form the multiple bond in order to get another structure with lower possible formal charge. Okay, so for these 2 oxygen, we didn't touch it, so it's still having the -1 formal charge. While for these oxygens that involve in double bond, okay, so this is the oxygens involved in double bond, I call it OA. So we need to calculate again the formal charge because previously in structure 1 is single bond, but in structure 2 it becomes double bond because one of the lone pair is being used to form the double bond. Okay, so we need to recalculate the formal charge. And for oxygen A, the valence electron is 6. So the lone pair electrons is 1, 2, 3, 4. So -4 plus. So for half bonding pair electrons, again, we can cut the bonding pair electrons half and only count the electrons that belongs to the oxygen, which is 1, 2. So 2 to give the formal charge for oxygen A equals to 0. So 0. Okay, so for bromine, we need to recalculate as well because now bromine, okay, so involved in the double bond. So how do we calculate the formal charge? Just use the formula. So valence electron 7 minus the lone pair electron 1, 2. So 2 plus half bonding pair electron. So cut all the bonding pair electrons into half and then only count the electrons that belongs to the bromine. So which is 1, 2, 3, 4. So 4 to give the formal charge equal to +1. So can you see that by use the terminal atom on one of the oxygen to form the double bond, you have structure 2 which has lower formal charge on 2 atoms. Okay, and then so any other structures that we can draw in order to give even lower formal charge on the atoms? Yes, we can use the lone pair on another oxygen to form the double bond in order to make the formal charge even lower, okay, closer to 0, okay? So this gives us the structure 3. So in structure 3, so this oxygen we didn't touch, so it is still having the formal charge equal to -1. And for this oxygen here, okay, it is same with the oxygens that we have calculated previously. So it will have the formal charge equals to 0. But for bromine, we need to recalculate the formal charge because now involved in 2 double bonds formation. So 7 valence electron minus lone pair electron 1, 2. So 2 plus. So the half bonding pair electrons, so cut all the bonding pair electrons to half and only count the electrons that belongs to bromine that involved in bonding. So that is 1, 2, 3, 4, 5. So 5. Can you see that now by forming 2 double bond, the bromine having 0 formal charge. So in structure 3, okay, so can you see that the formal charge on the atoms are lower possible? Therefore, structure 3 is the most plausible Lewis structure because lower possible formal charge on each of the atom. Okay, and then sometimes, okay, so structure 3, beside having the lower possible formal charge, that's why it is the most plausible Lewis structure, it is also the most plausible Lewis structure because the negative formal charge is on the more electronegative oxygen atom. So sometimes students tend to draw another structure for bromate ion. So students tend to draw this structure by using the terminal atoms on another oxygen to form double bond. But this is definitely not the most plausible Lewis structure of bromate ion because by drawing 3 double bond, you are having the negative 1 formal charge on bromine atom. Remember, the third priority, we must have the negative formal charge on more electronegative oxygen atom. Okay, so the more electronegative atom here is oxygen, so preferable to have the negative formal charge on oxygen instead of bromine. So because of that, so having 3 double bond using the lone pair on each of the oxygen terminal atom to form 3 double bonds will give you not the most plausible Lewis structure because you will get a structure where the negative formal charge is on less electronegative bromine atom. Okay, then now we move on to look at the common mistake made by students when draw the Lewis structure. So sometimes when want to make the multiple bond, students tend to use the lone pair on the central atom to make the multiple bond. Like for example, the bromate ion just now. So remember, to make multiple bond, we must use the lone pair from the terminal atom, not from the central atom. But sometimes students tend to make the mistake by using the lone pair on the central atom to make the multiple bond. So this is definitely wrong. It will not give you the most plausible Lewis structure. Must remember this. To make multiple bond, we must use the lone pair on the terminal atom, not from the central atom. So remember this mistake, okay, and not to do this mistake, okay. You want to make multiple bond, must use the lone pair on the terminal atom to make the multiple bond. So the second common mistake that students make is if the central atom is a period 2 element, you should not have more than 8 electrons around the central atom because for period 2 elements, there is no 2d orbital exists. So since there is no 2d orbitals, not possible for 2D for period 2 element when they become the central atom to have more than 8 electrons around them. Okay, so for example in ozone, okay, so to determine which structure is the most possible Lewis structure for ozone, again step number 1, we calculate the total number of valence electrons, and here we have 18 electrons. So in step number 2, we draw the skeletal structure, and then in step number 3, we make the terminal atoms octet. And then in step number 4, because after step number 3, our terminal atoms, okay, so can you see that there are 2 electrons remain? After we made the terminal atoms octet, in step number 3, we still have the 2 electrons remain, and these 2 electrons must go to the central atom. Okay, so after step number 3, can you see that our central atom, oxygen, is not yet octet? So this oxygen is not yet octet. So how can we make it octet? Again, in step number 4, we need to use the lone pair on the terminal atom to make the multiple bond in order to make the central atom octet. Okay. And then after step number 4, can you see that the formal charge for the first oxygen here, that having the single bond, the formal charge is -1, and the central atom, the formal charge of the oxygen is +1, and for this oxygen, another terminal oxygen that involved in double bond is 0. Okay, so this is actually the most plausible Lewis structure for ozone. Okay, and then sometimes students are being tricked because they tend to draw double bond. They tend to draw another double bond in order to make 0 formal charge on all the atoms. But this is actually wrong because by having another double bond, can you see that now around your central atom oxygen has more than 8 electrons. But oxygen is period 2 element. There is no 2D orbital exists to place the extra electron. Therefore, another double bond is not possible to be formed in ozone. Okay, so therefore, the ozone structure with 2 double bonds definitely is wrong. Okay, and therefore, the most possible Lewis structure for ozone is this one. Okay, it is the most plausible Lewis structure because it has the lower possible formal charge on all the atoms. So basically that's it for the Lewis structure. Then we move on to molecular shape and polarity. So for molecular shape, remember to determine the molecular shape of a molecule or polyatomic ion. So basically follow the valence shell electron pair repulsion VSEPR theory. In the theory stated that electron pairs around the central atom, they will repel each other. Therefore, in order to minimize the repulsion, they will arrange themselves as far apart as possible. And the order of the strength of the repulsion of electron pair around the central atom is in this order. So the lone pair repulsion is the greatest, followed by the lone pair bonding pair repulsion, and the bonding pair repulsion is the weakest. And how do we determine the molecular shape? So again, another 4 steps. So step number 1, you need to draw the Lewis structure. And in step number 2, you determine the total electron pair around the central atom. So by determining the total number of bonding pair and lone pair around the central atom, you can get the total electron pairs around the central atom. And from the total electron pairs, you need to determine the electron pair geometry. And this electron pair geometry is the backbone for us to draw the molecular shape. Okay, that's why it is very important in step 2 to determine the total number of electrons around the central atom. Then you determine the electron pair geometry in order for you to draw the molecular shape in step number 3, and then you can state the molecular shape. And in step number 4, if the question asks about the bond angle, you need to determine the type and also the strength of repulsion from the molecular shape in order to determine the bond angle. So for molecular shape, again, first we need to determine the electron pair. How do we determine the electron pair? From the bonding pairs and also the lone pair, we get the total electron pair. And then from the electron pair, we need to deduce the electron pair geometry, the backbone for us to draw the molecular shape. So for this, only 5 total electron pair and electron pair geometry you need to remember. So the first one is, if you get total 2 electron pair, the electron pair geometry is linear. So you draw the molecular shape based on the linear electron pair geometry. And if you get 3 total electron pair, so the electron pair geometry is trigonal planar. So you draw the molecular shape based on the trigonal planar. If you get 4 electron pairs in total, so the electron pair geometry is tetrahedral. So you draw the molecular shape based on the electron pair geometry tetrahedral. And if you get 5 electron pair around the central atom, so the electron pair geometry is trigonal bipyramidal. So trigonal bipyramidal. So you draw the molecular shape based on the trigonal bipyramidal electron pair geometry. So if you get 6 electron pair total around the central atom, so the electron pair geometry is octahedral, and you draw the molecular shape based on the octahedral, okay, based on the octahedral. So now we move on to look at if the question asks about molecular polarity, so what do we need to do? So basically, to determine the molecular polarity, you still follow through the 4 steps to draw the molecular shape, and then you add another step by going through the molecular polarity flow chart. Okay, so this is the molecular polarity flow chart. So if you get diatomic molecule, so you need to ask yourself one question. Are the atoms the same? So if yes, that means that there is no electronegativity difference between the 2 atoms. So means that you get non-polar molecule. But if you get the atoms are different, so like for example in HCl, 2 different atoms, so means that these 2 different atoms have different electronegativity. So therefore HCl is a polar molecule. For polyatomic molecule, you need to ask yourself two questions. So the first question is to ask whether the electron pair geometry is same with the molecular shape. So if yes, then you ask yourself the second question. Are the terminal atoms the same? So if yes, then you get non-polar molecule. Because it means that all the bond dipoles in the molecule can cancel out one another. So the molecular shape for the molecule is symmetrical. So the net dipole moment is therefore equals to 0. So you get non-polar molecule. But if the terminal atoms are not the same, like for example for this one, so you have bromine and also chlorine, so not the same. Then you will have a polar molecule. Means that the bond dipoles cannot cancel out one another. So if cannot cancel out one another, means that this molecular shape is not symmetrical. So if not symmetrical, then the net dipole moment is not equal to 0. So you get a polar molecule. So now we back to the first question. So if the first question, your electron pair geometry is not the same, it's different with the molecular shape. So if different, then you need to ask yourself the second question. Is it square planar or linear? So if it is square planar or linear, then again you get non-polar molecule. So why non-polar molecule? So assume X is more electronegative. So can you see that in this linear shape? So the bond dipoles can actually cancel out one another. So when can cancel out one another, so means that this linear molecular shape is symmetrical. So the net dipole moment therefore is equal to 0 and you get non-polar molecule. So as in square planar, assume X is more electronegative. So can you see that all the bond dipoles, so they can cancel out one another. So means that in square planar, you also get a molecular shape that is symmetrical. So therefore, the net dipole moment is equals to 0. You get non-polar molecule. However, if the molecular shape is not square planar or linear, then you will get a polar molecule. Why? Because the bond dipoles cannot cancel out one another. So means that the molecular shape is not symmetrical. So if it is not symmetrical, means that the net dipole moment is not equals to 0. Therefore, you get a polar molecule. So now we move on to look at the examples. So if the question asks you to determine the molecular shape, so how do you determine the molecular shape? So first draw the Lewis structure. So to draw the Lewis structure, you need to calculate the total number of valence electron and then draw the skeletal structure. So carbon less electronegative than chlorine, so it becomes the central atom. So this is your skeletal structure. So and then need to, so I have drawn 8 electrons, so minus 8, so 24 electrons remain. So we continue. Need to measure the terminal atoms octet. So to make the terminal atoms octet, so I have drawn all the 24 electrons, so no electrons left to be put on the central atom. So this is the Lewis structure for CCl4. So that is step number 1 to determine molecular shape. So step number 2, we need to determine the electron pair geometry. So to determine the electron pair geometry, we need to look at our central atom carbon here. Around carbon, there is no lone pair, so 0 lone pair. How many bonding pairs? So 1, 2, 3, 4. So we have 4 bonding pair. So therefore, the total electron pair equals to 4, because 4 plus 0, we get 4. So for total electron pair equals to 4 around central atom, that will give us the electron pair geometry equal to tetrahedral. So in step number 3, when we want to draw the molecular shape, we must draw based on the backbone tetrahedral. So this is a tetrahedral shape. So we put in our molecule. So this is the molecular shape of CCl4, and this molecular shape is tetrahedral. So this molecular shape is tetrahedral. So how do we determine the bond angle? So to determine the bond angle again, we need to determine the type and also the strength of repulsion based on the molecular shape. So from the molecular shape here, we know that we have 4 bonding pairs, and these 4 bonding pairs, they will repel each other equally to give the bond angle 109.5. So bond angle is the angle between bonding pair. So means that here is 109.5 degree, the bond angle. Then how do we determine the molecular polarity of CCl4? So to determine the molecular polarity of CCl4, we must determine from the molecular shape. So this is our molecular shape. So first, we can draw the bond dipoles first. Between carbon and chlorine, chlorine is more electronegative. Since chlorine is more electronegative, so when we draw the bond dipoles is pointing towards chlorine. So can you see that? Okay, so the bond dipoles are pointing toward chlorine, so means that chlorine is more electronegative than carbon. So how do we determine whether this CCl4 molecule is polar or non-polar? So we just need to go through the flow chart. Okay, ask ourselves 2 questions. So the first question, is the electron pair geometry same with the molecular shape? Yes. Remember just now the electron pair geometry is tetrahedral, and the molecular shape we determine is also tetrahedral. So means that the answer for the first question is yes. So if yes, then we move on to ask ourselves the second question. So are the terminal atoms the same? So here we have chlorine, 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 chlorine. So all the terminal atoms are the same. So yes, so means that our CCl4 is a non-polar molecule. So why non-polar? It is because all the bond dipoles can be cancelled out, and the molecular shape for CCl4 here is symmetrical. Therefore, the net dipole moment is equals to 0, and the CCl4 therefore is a non-polar molecule. So then now we move on to look at the second example. So determine whether CHCl3 molecule is determine the molecular shape of a CHCl3. Okay, so to determine the molecular shape, again, first we need to draw the Lewis structure. So to draw the Lewis structure, we need to calculate the total number of electrons. So total number of valence electrons here is 26. So and then the carbon, okay, is the central atom. So this is the skeletal structure for CHCl3. And then remember, we need to make the terminal atoms octet. Okay, so I have drawn 8 electrons, so minus 8. So 18 electrons remain. Okay, so measure terminal atom. Chlorine is octet. Okay, so minus 18. So 0 electrons left. So means that there will be no electron on the central atom. Okay, so no lone pair on the central atom carbon. Okay, and then we can move on to step number 2, determine the electron pair geometry. So carbon, our central atom, around carbon, there is no lone pair, but there are 4 bonding pair. 1, 2, 3, 4. 4. So to give us the total electron pair around central atom equals to 4. So therefore the electron pair geometry again is tetrahedral. Tetrahedral. So in step number 3, when we want to draw the molecular shape for CHCl3, we must draw based on tetrahedral backbone. Okay, so put CHCl3 in, so we get something like this. Okay, so this molecular shape is also tetrahedral. Okay, it's also tetrahedral. And instead, number 4, we want to determine the bond angle in CHCl3. So to determine the bond angle, we need to determine the type of repulsion and also the strength of repulsion. So here we have 4 bonding pairs. They repel each other equally. So again, the bond angle is 109.5 degree. So again, it is still 109.5 degree. Okay, so that is the bond angle. Then how about the molecular polarity for CHCl3? So for CHCl3, okay, to determine the molecular polarity, we can start with drawing the bond dipoles. So between carbon and hydrogen, so carbon is more electronegative. So therefore, the bond dipoles is pointing toward carbon. Okay, and between carbon and chlorine, chlorine is more electronegative. That's why later on when we draw the bond dipole, it must point towards chlorine. So these are the bond dipoles in CHCl3. So how do we determine the molecular polarity? Again, need to go through the flow chart. So the first questions that we need to ask ourselves is whether this molecule having the electron pair geometry same with the molecular shape. So remember just now we have determined CHCl3 having the electron pair geometry tetrahedral and the molecular shape is also tetrahedral. So therefore, the answer for question number 1 is yes. So if yes, then we move on to ask ourselves the second question. Are the terminal atoms the same? So can you see that here we have chlorine, chlorine, and also hydrogen. So means that they are not all the same. So if not all the same, okay, so the answer would be no. So means that CHCl3 is a polar molecule. So why polar molecule? It is because the bond dipole, so these 4 bond dipoles, they cannot cancel out each other. So when they cannot cancel out each other, the molecular shape therefore is not symmetrical. As the bond dipoles cannot cancel out each other, so the molecular shape is not symmetrical. So the net dipole moment therefore would be not equals to 0. Since it is not equals to 0, means that CHCl3 is a polar molecule. So now we move on to look at the third example. So to determine the molecular shape of ICl3. So to determine the molecular shape of ICl3, remember, follow through the 4 steps. Step number 1, we draw the Lewis structure. So to draw the Lewis structure, first we calculate the total number of valence electron. And in ICl3 is 28. So, and then we need to draw the skeletal structure. So iodine is less electronegative than chlorine, therefore it becomes the central atom. So this is the skeletal structure for ICl3. So I have drawn 6 electrons. So minus 6, so 22 electrons remain. So, and then need to measure the Cl terminal atoms octet. So by making the terminal atom Cl octet, so I have drawn another 18 electrons. So 4 more electrons left, and this remaining electron we must put at the central atom. So put at the central atom iodine. So this is the Lewis structure for ICl3. And to determine molecular shape, the second step, we need to determine the electron pair geometry. For that, we need to determine the number of bonding pairs and also lone pairs around the central atom iodine. So around central atom iodine, there are 2 lone pairs and 1, 2, 3, 3 bonding pairs. So total electron pair around the central atoms are 5. Okay, so this gives electron pair geometry trigonal bipyramidal. Means that when we want to draw the molecular shape ICl3, we must draw it based on the backbone trigonal bipyramidal. So this is the backbone trigonal bipyramidal. So in trigonal bipyramidal, the equatorial plane having the angle 120 and the axial is 90 degrees. Okay, and then in ICl3, we have 2 lone pair. Remember in the VSEPR theory, in order to minimize the repulsion, the electron pair must stay as far apart as possible. So in trigonal bipyramidal, can you see that in order for the lone pair to stay as far apart as possible, they should go to the equatorial plane with the angle 120 degrees. Okay, so because of that, so this is the molecular shape of ICl3 with the lone pair going to the equatorial plane so that the repulsion in ICl3 is minimal. So for this, we get the molecular shape T shape. So can you see the letter T? So T shape. So this molecular shape in ICl3 is therefore T shape. So we have done with step number 3. So if the question continue asking about bond angle, you need to determine the type and the strength of repulsion. Then only you can state the bond angle. Okay, so in ICl3, you can see that there are 2 lone pairs. So these 2 lone pairs, they will repel each other. And the lone pair repulsion is the greatest, followed by the lone pair bonding pair repulsion, followed by the bonding pair repulsion. Okay, so due to this order of bond strength, this order of the strength of repulsion, therefore the bond angle would be less than 90 degrees. Okay, would be less than 90 degrees because the lone pair repulsion is greatest, followed by the lone pair bonding pair repulsion. So squeeze the angle between the bonding pair to be less than 90 degrees. So to determine the molecular polarity of ICl3, so we need to determine based on the molecular shape. So based on the molecular shape. So before we go through the flow chart, we can draw the bond dipoles first. Between iodine and chlorine, chlorine is more electronegative. Therefore, the bond dipoles is pointing towards chlorine. And to determine whether ICl3 is polar or non-polar, again, we go through the flow chart. So So the first questions that we need to ask ourselves is whether the electron pair geometry is same with the molecular shape. So in this ICL3, it is different. Remember, the electron pair geometry is trigonal bipyramidal, while the molecular shape is T-shape. So since it is different, so the first question answer is no. Then we need to ask ourselves, is this molecular shape square, planar, or linear? So we already determined it is T-shape. So of course the answer for question number 2 is also no. So if no, that means that ICL3 is a polar molecule. So why polar molecule? It is because these 3 bond dipoles, they cannot cancel out each other. When they cannot cancel out each other, means that this ICL3 T-shape, the T-shape for ICL3 molecule is not symmetrical. Since it is not symmetrical, the net dipole moment is therefore not equals to 0. And when the net dipole moment not equals to 0, means that ICL3 is a polar molecule. So done with example 3. So we move on to look at the example 4. So in example 4, how do we determine the molecular shape of SEF2? So again, first we draw the Lewis structure. So the total number of valence electrons here is 22. So Xe is less electronegative than fluorine, so it will become the central atom. And then fluorine, the terminal atom. So this is the skeletal structure for SEF2. So I have drawn 4 electrons. So 18 electrons left. And then need to measure the terminal atom fluorine octet. So put in another 12 electrons. So 6 electrons remain. So these 6 electrons remain must put as the lone pair on the central atom. So this is step number 1. So draw the Lewis structure for SEF2. Then we can move on to step number 2, determine the electron pair geometry. So to determine the electron pair geometry, first we need to determine around our central atom, there are how many lone pairs and bonding pair. So for lone pair, there are 1, 2, 3. So 3. So for bonding pair, 1, 2. So 2. So total electron pair around the central atom therefore is 5. So for 5 electron pair, the electron pair geometry therefore will be trigonal bipyramidal. Trigonal bipyramidal. So to draw the molecular shape, we must draw it based on the trigonal bipyramidal backbone. So again, now we have 3 lone pair. So in trigonal bipyramidal, okay, so the equatorial plane, the angle is 120, while the axial again is 90. Therefore, in order to minimize the repulsion, the 3 lone pair here must go to the equatorial plane so that the repulsions can be minimum. So this gives us the molecular shape like this. Okay, and can you see that this is linear? So this molecular shape is linear. Okay, so if want to determine the bond angle, we must take into account the type and also the strength of repulsion. So here we have 3 lone pairs, and the 3 lone pairs will repel each other, and the lone pair repulsions is the greatest, followed by the lone pair bonding pair repulsion, and the bonding pair repulsion is the weakest. Okay, and this will result in the angle between the bonding pair to be 180 degree. Okay, so therefore the bond angle for this molecule is 180 degree. So to determine the molecular polarity, we need to determine the molecular polarity based on the molecular shape. So for this, first we must draw the bond dipoles first between Se and fluorine. So fluorine is more electronegative. Therefore, the bond dipoles should point towards fluorine. And then in order to determine whether SEF2 is polar or non-polar molecule, we go through the flow chart. So for this, we need to ask ourselves the first question, is the electron pair geometry same with the molecular shape? So for this, it is not the same. Remember, the electron pair geometry is trigonal bipyramidal, but the molecular shape here is linear. So it's not the same. So no. And then the second question you need to ask yourself is it square planar or linear? For this question, it is linear. This molecule, it is linear. So if it is linear, the second question answer is yes. So if yes, then you get non-polar molecule. Non-polar molecule. So why non-polar molecule? It is because these two bond dipoles, they can cancel out each other. Okay. Since the two bond dipoles can cancel out each other, so means that this linear shape is symmetrical. So when it is symmetrical, therefore the net dipole moment would be equals to 0, and SEF2 therefore is a non-polar molecule. So that's it for the fourth example. So basically, that's it for my sharing for tonight. So now we can move on to the Q&A section. Uh, so the first question from Jude. So is it okay if we complete the octet for AL? So it depends on the question. So sometimes if the question asks why AlCl3, okay, so when it is the most plausible Lewis structure or more stable when having incomplete octet, then you need to draw both. Actually, you need to draw AlCl3 in complete octet form and also in the octet form. Okay, and then from there you discuss using the formal charge. You calculate. The you can calculate. Okay, so which one have the lower possible formal charge, and you will see the AlCl3 with the incomplete octet have the lower possible formal charge. So if the one with lower plausible formal charge, therefore it will be the more plausible Lewis structure. Okay, so Jude, okay, so Jiajun, okay, so actually we need to write the formula below the element. Yes, you need to, after you calculate, you need to write the formal charge. So just now, because I make it in the PowerPoint, I already wrote it, so I just played it. Yes, you need to write it. After you calculate, you need to write the formal charge below that particular atom. Yes. To show the number of bonding and bonds to one atom, right? Okay. So basically half. Okay. So half in the formula, charge formula, it actually refer to first you need to understand what is formal charge. Formal charge basically is the charge of the atom when the electrons in the bonding pairs are equally shared. That's why the formula is half. That's why when if you do not if you want to use the half, then you need to calculate all the bonding pairs electrons, then only you half it. If not, then you just use my method. So you cover half and only count the electrons that belongs to the atom that involved in bonding. Are you clear? White hole, no. Okay, not all the central atom BeBal will have incomplete octet. Like for example, AlCl4 minus, AlCl4 minus, then the aluminium will be octet. It depends on the question. If the question asks most plausible Lewis structure and asks you to determine the most plausible Lewis structure, yes, you need to show the working for formal charge calculation. But if the question not asking directly where to ask you choose which one is the most plausible Lewis structure, you actually do not need to show. Okay, but if you are not sure, then you just show. Yes, you can subscribe it with ABC. Yes, you can. But make sure you label on your Lewis structure and also in your formal charge calculation. Okay, so for your question, okay, Aina, for the ozone, if your central atom is period 2 element, not possible to have expanded octet. So you cannot have the drawing with more than 8 electrons around it. But then, like for the Br03 minus, just now, bromine is a period 4 element, so it can have expanded octet. Then possible for it to form multiple bonds. Then, if possible to form multiple bonds, so which one is the most plausible Lewis structure? You need to determine through the formal charge calculation. Yes, electron. Okay, how to determine which? Okay, again, the central atom must be the least electronegative atom, paling kurang electronegative atom. Okay, paling kurang electronegative. So just need to remember your chapter 3. Across the period from group 1 to group 17, elements become more electronegative, Why? Because the effective nuclear charge increases, size becomes smaller, easier to attract the electron. That's why across the period, the element become more electronegative. You just need to remember the trend, then you can determine. And then going down the group, it becomes less electronegative because size getting larger, so harder to attract electrons. Okay, so in the bromate ion Br03 minus, you calculate the formal charge, right? So just now I calculated the formal charge, and you see that the formal charge is so big, okay, it's large. In order to get the more plausible Lewis structure, you need the formal charge to be lower possible. The formal charge on each atom to be lower possible. Okay, so because of that, in order to make the formal charge lower possible, you need to form the multiple bond until you get the most plausible Lewis structure. There are 4 bonds or count the rest. I don't get your question. Make sure that there are 4 bonds or count the rest. And lastly, add. Oh, you mean for the electron pair? You mean the electron to determine the total electron pairs around the central atom? So if for the total electron pair around central atom, you just need to calculate how many group of bonding pair. So if like 4 bonding pairs, 1 lone pair, then total will be 5 electron pair. Remember, the VSEPR theory is the electron pairs that will determine the molecular shape. Okay, so because they all involved in the repulsion, so you can calculate the bonding pair first, and then you calculate the lone pair around the central atom, or the other way around. You calculate the lone pair first, and then only you count the bonding pair. Either one will give you same answer. possible. No, when you draw the Lewis structure, you haven't applied the VSEPR theory. Okay, you just draw the Lewis structure. Okay, and then from the Lewis structure, only you determine the electron pair, total number of electron pair, the electron pair geometry, and then you draw the molecular shape. That part you apply the VSEPR theory. But for Lewis structure, no, you don't need to apply the VSEPR theory. So means that you don't need to draw your Lewis structure according to the shape. No. Yeah. The AX2 or AB2, they are the same. Okay, good. So if want to determine the molecular polarity, you need to start draw from Lewis structure until you get the molecular shape, and then you determine the molecular polarity based on the molecular shape, not Lewis structure. Molecular polarity you deduce based on the molecular shape, but you still need to draw the Lewis structure first. That is the first step in order for you to draw the molecular shape. Oh, okay. So this one I already mentioned. So you just need to remember the trend in the periodic table across the period from from the left to the right. Elements become more electronegative because proton number increases, effective nuclear charge increases. So the tendency to attract electrons becomes stronger. So means that across the period, the element becomes more electronegative. So for this, you just need to determine the period and the group of the element. And then from there, you can roughly guess, okay, which one is less electronegative. So less electronegative, it will be the central atom when you draw the Lewis structure. Yeah. So basically, the electron pair geometry or basic molecular shape or electron pair arrangement. So these three terms, they can be used. They can be used, okay. But sometimes the questions ask electron pair arrangement. Sometimes they say electron pair geometry. Sometimes they say basic molecular shape or basic molecular geometry. You just need to know basically they refer to the same thing. If the question asks for Lewis structure and the question there stated 1 mark, you just draw one Lewis structure. But if the question, okay, giving you one molecular formula, but the question is like 5 marks, so means that there are more than one Lewis structure. So means that you need to draw the possible Lewis structure and then determine which one is the most possible Lewis structure. You need to look at the question to answer. If 1 mark, you just write 1. Yeah. They are possible to have the central atom that excluded from octet. Remember, in complete octet, we can have beryllium, boron, and aluminium become the central atom, and then when those three elements become the central atom, possible for you to have incomplete octet. So if that is the case, when you draw you draw the molecular shape, definitely you have less than 8 electrons around central atom. Okay, that's why you need to go through the flow chart. Remember the flow chart I showed you just now? Ask yourself two questions. The electron pair geometry, whether it is same with the molecular shape. Okay, if yes, then what you need to do. If no, it will lead you to polar or non-polar. If you get polar, means that the bond dipoles cannot cancel out each other. And definitely you get the molecular shape being not symmetrical. That's why the net dipole moment is not equals to zero, and you get the polar molecule. You use the flow chart to guide you. Oh, if the questions ask about Lewis structure, you don't need to draw the molecular shape, just draw the Lewis structure. Better not, okay? So better not, you still need to draw the Lewis structure and then only you draw the molecular shape, okay? You not really. Not really. You don't need to memorize. You have learned chapter 2. You already learned the usually the questions will give you the proton number. They will give you the proton number. So from the proton number, you just need to write out the electronic configuration. So from the electronic configuration, you can determine the number of valence electron. So with the number of valence electron, then you can calculate the total number of valence electron and you can do the rest. For the molecular shape, with or just the for molecular shape, the Lewis structure must be most usually to draw the molecular shape, you need to if the question asks Lewis structure first, okay, usually you need to draw your molecular shape from the most plausible Lewis structure. You need to draw from the most plausible Lewis structure. Oh, okay. So for this one, you just need to determine how many bonding pair and lone pair around the central atom. So if you have two bonding pair, three lone pair, then you get a linear shape. So if you have three bonding pair, two lone pair, you get T shape. Okay, so for chlorine and oxygen, you just need to remember FON, fluorine, oxygen, and nitrogen, these three elements, they are in period 2 and then more to the right. Okay, so fluorine being the most electronegative element, followed by oxygen, and then followed by nitrogen. And then for the group 17 element, going down the group, it becomes less electronegative. How many you need to draw? You need to look at the mark. If the mark's 3, then you draw 3. So if the mark's 5, you draw 5. If the mark's 1, you draw 1. That is the clue actually. Basically, the resonance structure are basically the most plausible Lewis structure is just one. The most stable, most plausible Lewis structure is just one. But you can draw many resonance structure. But only one, or if for some element, some ion or some molecule, there can be two. most plausible Lewis structure, but usually it's just one. And between them, there are resonance structures to one another. Among the resonance structure, you choose one structure being the most plausible Lewis structure, but sometimes you can have two or three. Okay, so you just need to remember this one is chapter 2. So chapter 2, remember this one is alpha principle. So alpha principle, you just need to remember 1s, 2s, and then 3s, 3p, 3d, and then you draw the line diagonally. You draw the line diagonally. That is how you remember the alpha principles. The order of the energy level of the orbitals. Okay, you just need to write 1s, 2s, 2p, 3s, 3p, 3d, and then draw the arrows diagonally. Okay, so oxygen period 2, bromine period 4. So oxygen is when you write the electronic configurations, right? Oxygen period 2, so definitely smaller. When smaller, oxygen smaller, so definitely it's more electronegative. Smaller, bromine bigger. So bigger size, less electronegative because harder to attract electrons. Oh, yeah, welcome. So hopefully the sharing tonight is helpful to you. Mm. Mm. Yeah, welcome. uh, so for molecular shape, right? So basically, you need to learn how to draw. When you know how to draw, easier for you to remember. You need to remember how to draw the basic molecular shape or electron pair geometry first. When you can draw the five basic molecular geometry: linear, trigonal, planar, tetrahedral, trigonal, bipyramidal, and octahedral, then very easy for you to remember the molecular shape, because the molecular shape is deduced from the electron pair geometry. You just need to remember the basic molecular geometry or electron pair geometry, and then after that, if there is a lone pair, you just need to remove one and then you put the lone pair in, and then you look at the bonding pair. They give you what shape? They give you what shape? Then that will be the molecular shape of it. So first you must remember the five basic molecular shape or electron pair geometry first. Then easier for you to learn the molecular shape easily. Yeah. Resonance and the most plausible Lewis structure, they are related to one another. So again, most plausible Lewis structure refer to paling stabil punya Lewis structure. But among them, yang you lukis banyak-banyak itu, they are resonance structures to one another. They are resonance structures to one another. But among them, it might be one or two most plausible Lewis structure. We need to draw like yes, you need to draw the Lewis structure, but you don't need to calculate the formal charge if they don't ask which one is the most plausible Lewis structure. You can draw the resonance structure. You just basically draw all the possible Lewis structure. So that would be polar. Oh, Okay, so because there is something that you didn't learn, okay, so basically for the 4s and 3D subshell, they are very close to one another. Their energy level are very close to one another. And what happened is once the 3D orbitals been filled with electron, it will push the 4s orbitals to higher energy level because the 4s orbitals are being pushed to higher energy level. That's why some book write 3D first, then 4s. Okay, but there 4s still being filled first. Okay, because 4s lower energy, lebih rendah the energy level. But after 3D being filled, it can push 4s to higher energy level. That's why some book write 3D 10 first, then only 4s. But some book write 4s first because 4s still lower energy than 3D. That's why it will be filled first. Oh, later on I share my PowerPoint in the Telegram group. Is it okay? Okay, good. All the best, okay, everyone. Uh, Not to say that to write the 3D first. Actually, if you write the 4S first and then only 3D is still correct. It's still correct. Okay, because that is according to the alpha principle. You fill the lower energy orbital first before filling the higher energy orbitals. It's just that after 3D being filled, it can push 4S to higher energy level. That's why some book write it the other way around. Yeah. But if we can remember to move electrons correctly. Yeah. That's why after forming ion, electron will be removed from the 4s first because after being filled with electron, 4s is actually higher energy. It's up to you which one easier for you to remember. Yes, long pair repulsions will definitely be stronger because long pair not involved in bonding closer to the central atom. So if closer to the central atom and both of them having the same charge, so the repulsion definitely is the strongest. Mm. It's all right. It's all right. The bond angle. Uh, you mean you need to write bond angle. If not, nobody is going to know the less than 90 degree is referring to what. You need to write bond angle equals to less than 90 degree. Mhm. Just write the bond angle, then write less than 90 degree. Oh, exam please write. Yeah. You need to write LP represent what first, and then you can use LP. But then if you didn't state, then please write long pair repulsion. If not, you are going to get it wrong. Mhm. Good.
Terima kasih kepada Puan Mdm Tang untuk sharing perkongsian tajuk Chemical Bonding Part 1, lebih structure dan molecular shape. So harap perkongsian malam ni membantu para pelajar untuk membuat ulang kaji terhadap chapter 4 Chemical Bonding. So untuk siri kedua, Chemical Bonding ialah 4.3 hybridization orbital overlapping akan berlangsung di Sabtu ini. So kita jumpa nanti pada malam Sabtu. Okay, terima kasih semua pelajar. Jangan lupa isikan borang soal selidik yang dipin di dalam live chat YouTube. So semoga pelajar dalam keadaan baik dan boleh membuat ulang kaji dengan hati yang tenang. So sebelum berakhir di sesi ini, kita berjumpa Mdm Tang untuk memberi ucapan kepada pelajar untuk yang sedang menduduki PSP study week untuk PSPN.
Okay. So students, you all can do it. All the best, okay? All the best. All the best, okay? Bye-bye.
So harap sabar pelajar kita mahal tapi sedikit masalah teknik.
Huh? Oh.
Okay, sekarang kita berjemput Mdm Tang untuk memberi sepatah untuk para pelajar sekalian.
Okay, so students, you all can do it. All the best, okay?
Okay, jumpa lagi terima kasih kepada semua pelajar yang menonton malam ni. So kita jumpa lagi pada hari Sabtu dan akan datang. So sila sentiasa follow maklumat dari Telegram Magic Revision Siri 2. Terima kasih, bye.
Bye-bye.